ocean covers more than 2/3 of our planet. Yet most of it remains unseen, untouched, and unknown. And the further you descend, the stranger the world becomes. Light disappears long before life does. Pressure rises long before hope fades. And somewhere in that frozen black void, nature begins rewriting its own rules. This is the deep sea, Earth's largest, oldest, and most mysterious ecosystem. A place where survival demands creativity, patience, and anatomy that defies everything we think we know about biology. But among its many mysteries, one stands taller, literally, than the rest. Why does the deep create giants? Giant isopods the size of puppies, jellyfish wider than a car, squid as long as a school bus. Creatures that look more like alien organisms than anything born on Earth's oceans. For over a century, scientists have tried to explain this phenomenon. They've studied pressure, temperature, oxygen, body structure, metabolism, and energy cycles. And yet, the full reason remains a puzzle with missing pieces. Today, we're diving straight into the abyss to understand why the deep sea turns ordinary animals into towering giants. How those giants survive in one of the harshest environments on Earth. And what their existence tells us about evolution and about the future of life on this planet. Imagine leaving the surface world behind. Boats, waves, sunlight, all swallowed by a growing, chilling silence. As you sink below 200 meters, colors fade. Red vanishes first, orange next. By 500 meters, blue dominates everything, casting the world in a dim, eerie glow. By 1,000 meters, sunlight is gone forever. This is the midnight zone. A world without morning, without evening, without seasons. A world where darkness is not a condition. It is the law. The temperature drops close to freezing. The pressure reaches crushing levels, enough to collapse submarines if not engineered perfectly. Every extra meter down adds more force, more weight, more danger, and yet, something remarkable happens here. Life doesn't stop. Life adapts. And in many cases, life grows big. The first creature that greets you looks familiar, but only at first glance. A giant isopod, one of the deep sea's most iconic giants. Imagine a pillbug, those small insects that curl into balls. But now, imagine it inflated to the size of a small dog. Thick armored plates, powerful legs, eyes adapted to low light, and a body built to survive almost a year without food. Next, a shadow drifts by. It pulses like a slow heartbeat. A jellyfish, over a meter wide, moving through the water with the patience of a glacier. Its body glows faintly, its arms thick and fleshy, drifting behind it like ribbons of red smoke. Further away, something larger, much larger, a colossal squid, the deep's most feared and elusive giant. Eyes so large they can detect faint bioluminescent twinkles from miles away. Tentacles lined with rotating hooks, a body capable of wrestling sperm whales in battles that scar both creatures for life. These aren't exaggerated sea monster myths. These are real animals, measured, studied, preserved, and documented. And the deeper you go, the more the scale warps. Shrimp become giants. Amphipods grow to the size of your hand. Worms stretch meters long. Jellyfish expand into billowing, ghost-like shapes so big they look unreal. So why here? Why the deep? Why would a world of cold, darkness, and scarce resources favor size? The first key to gigantism is hidden in the temperature. Down here, water rarely rises above 4 degrees Celsius. That cold reshapes everything. Cold slows chemical reactions. It slows heartbeat, digestion, energy use, and movement. In most ecosystems, slow metabolism is a disadvantage. Predators become faster. Competition becomes fiercer. Life demands speed. But in the deep sea, slow means efficient. Slow means survival. Slow means you burn fewer calories and live longer between meals. A giant isopod can sit motionless on the ocean floor for weeks, even months, waiting for something edible to drip down from above. A fish corpse, a squid, a random piece of organic matter. The deep sea doesn't reward speed, it rewards patience. Cold water also holds more dissolved oxygen. This is important. Larger bodies need more oxygen to function. In warm tropical waters, oxygen becomes a limiting factor. Big bodies suffocate faster. But in cold, deep water, there's just enough oxygen to support massive size. Being big is suddenly possible. Pressure in the deep sea is unimaginable. At depths of 4,000 meters, the pressure reaches over 400 atmospheres, the equivalent of placing dozens of elephants on every square inch of your body. This pressure shapes evolution. Smaller creatures have more surface area relative to their volume, meaning pressure affects their cells more intensely. Larger animals have more internal volume compared to surface area, making them more stable under extreme pressure. In simple terms, bigger bodies deform, less smaller bodies get crushed easier. Over millions of years, the deep sea gradually selects for animals that can resist pressure, and size becomes an advantage. But if the deep is so food poor, why evolve large bodies at all? Shouldn't smaller be easier? Counterintuitively, the deep sea reverses that logic. Food doesn't arrive regularly. Only small flakes of organic debris called marine snow and occasional large carcasses. Smaller animals need more constant feeding to survive. Giants, however, can store fat, move slowly, and use energy far more efficiently per gram of tissue. The result? Being big actually conserves energy over decades. This is why many deep-sea giants live exceptionally long lives. The Greenland shark, for example, matures at 150 years old and may live past 400 times, moves differently in the deep, slow, stretched, almost frozen. In the sunlit oceans, predators are everywhere. Sharks, dolphins, swordfish, barracudas. The surface and mid-water layers are battlegrounds filled with fast hunters and faster prey. Down here, that chaos doesn't exist. Predators in the deep are rare, specialized, and built for one specific method: ambush. The anglerfish waits motionless for hours, its glowing lure twitching like a worm. The dragonfish uses invisible red light that most species can't see, to scout prey like a sniper hidden in total darkness. The gulper eel opens its jaws so wide it could swallow something its own size. But none of these predators are built for speed or endurance. Energy is far too precious for that. This creates an unusual evolutionary situation. If predators are slow, spread out, and energy limited, being large becomes safer. A giant isopod's thick armor makes it not worth the effort. A big red jellyfish's sheer mass makes it nearly impossible to swallow. A colossal squid's hooks and muscle power, combined with its size, turn it into a creature even a sperm whale doesn't attack casually. The deep sea rewards creatures that are too large to kill efficiently. In an environment where every calorie counts, predators won't waste energy on prey that's too big to subdue, too armored to break, or too slow to chase anyway. So size becomes protection. Size becomes survival. Most environments on Earth shift constantly. Seasons, storms, temperature swings, currents, nutrient cycles, migration patterns. But the deep sea is the closest thing we have to a timeless world. No sunlight, no seasons, no significant temperature change, no sudden storms, no dramatic ecological revolutions. For millions of years, conditions down here have remained almost exactly the same. Evolution in the deep plays the long game. No rush, no sudden pressure to adapt, no rapid extinction events tearing ecosystems apart. This stability allows animals to evolve slowly, refining traits across unimaginable spans of time. Some deep-sea species are practically living fossils, barely changed since the age of dinosaurs. Lineages like giant isopods, deep amphipods, and tube worms have had millions of years to experiment with size. And because nothing disrupts their world, their giant forms persist. In an unstable environment, giants often go extinct. In a stable environment, giants thrive. Life in the deep depends on one thing: what falls from above. There are no plants, no algae, no sunlight, no photosynthesis. Everything alive in the deep is powered by dead material sinking from the surface, marine snow. Marine snow isn't beautiful. It's a slow blizzard of decay. Flakes of dead plankton, bits of fish scales, fecal pellets, fragments of jellyfish, and the remains of creatures torn apart in the upper layers. Most of it is eaten long before it reaches the abyss. What survives the descent is barely enough. But every once in a while, the deep receives something extraordinary: a whale fall. When a whale dies and sinks, it becomes a biological jackpot. Tons of nutrient-rich flesh hitting the ocean floor like a bomb of life. One whale fall can feed an entire community for years. And this is where giant scavengers shine. Their large bodies allow them to detect, store, and use energy with incredible efficiency. A giant isopod can gorge when food arrives, then survive months of famine. Giant amphipods swarm a whale carcass in enormous numbers, stripping it clean with terrifying precision. Being small in this world is not efficient. Being big is. Deep-sea gigantism isn't just about size. It's about survival strategies crafted over millions of years. 1. Slow metabolism. Most deep-sea giants move with extreme calm. They drift, glide, or crawl. Movement is measured in careful doses. Every twitch costs energy they cannot afford to waste. 2. Energy storage. Large bodies store fat and nutrients for years. They can enter near hibernation states between meals. 3. Delayed reproduction. Many giants reproduce late in life. Why rush when nothing in your environment changes? Slow environments produce slow life histories. 4. Low predation pressure. Giants survive because predators are rare. Evolution is free to experiment with size, shape, and longevity. 5. Longer lifespans. Slow metabolism increases lifespan dramatically. The Greenland shark may live longer than entire human civilizations. These strategies aren't choices. They are the only way to survive a world where food is a luxury and movement is a gamble. Despite decades of research, much about deep-sea gigantism remains unexplained. Why do some lineages become giants while others stay small? Why do amphipods grow 30 times larger in trenches? Why do we see radical size shifts between shallow and deep relatives? Scientists have theories, but no single explanation fits every creature. The deep sea is too vast, too unexplored, too secretive. We've mapped the surface of Mars better than we've mapped our own ocean floor. Every time a submersible descends into the unknown, it finds something new, something that doesn't fit our rules. A jellyfish the size of a person, a squid with arms thicker than rope, a worm that stretches like a serpent, creatures with transparent skin, glowing organs, or impossible shapes. The deep doesn't just challenge biology, it challenges imagination. For centuries, sailors told stories of monsters in the sea. Kraken tearing ships apart, serpents coiling through waves, giant shadows rising from the deep. Most of those stories came from rare encounters with giant squid or decayed deep-sea creatures washed ashore. Imagine being a sailor in the 1700s and seeing a colossal squid corpse drifting beside your ship, eyes bigger than fists, tentacles covered in hooks, body stretching longer than your mast. Of course, they thought it was a monster. The truth is less violent but far more fascinating. These creatures aren't monsters. They are survivors, adaptations of physics, chemistry, scarcity, and time. The ocean didn't create monsters. It created experts, animals engineered by millions of years of pressure, cold, and darkness. Here's the unsettling truth. We've explored less than 5% of the deep ocean. That means more than 95% remains untouched, unseen, unmapped. If the giants we've already discovered are this extreme, what lies in the remaining dark? Bigger squid? Unknown crustaceans? Creatures longer, wider, stranger than anything we've imagined? Every expedition finds something new, something that pushes biology into unfamiliar territory. We haven't even come close to understanding the full scale of the deep's giants. To understand deep-sea giants, you need to look at how their bodies are built. Their anatomy isn't designed for speed or strength. It's engineered for survival under impossible conditions. Most deep-sea giants share several unusual traits: flexible tissues instead of rigid structures, low-density bodies instead of heavy skeletons, fluid-filled chambers to resist pressure, enzymes adapted to extreme cold, blood chemistry tuned for low oxygen. Take the colossal squid. Its body is mostly soft tissue, no bones to crack under pressure. Its muscles are designed for short bursts, not long chases. Its eyes, the largest in the animal kingdom, allow it to detect tiny flashes of bioluminescence from predators and prey alike. Or look at giant amphipods. Their bodies expand with fluid at depth. When brought to the surface, they shrink dramatically and often die instantly because their pressure-adapted design collapses without the weight of the deep. These creatures aren't big because the deep sea allows it. They're big because the deep requires it. In shallow waters, competition is loud, aggressive, constant. Coral reefs are war zones. Coastal waters are crowded. Rivers and shores are full of species battling for food, shelter, territory, mates. The deep sea is the opposite. It's not crowded, it's empty. But emptiness creates its own kind of competition. In a world where resources are scarce, you survive not by fighting, but by lasting longer than everything else. The winners are those who can endure. Weeks without food, months of stillness, years of slow growth. This silent competition naturally favors creatures that can stretch time, not outrun it. And the best way to stretch time? Grow large, move slow, and store energy like a living battery. Time in the deep sea moves differently. On the surface, life speeds forward at a frantic pace. Creatures grow fast, breed fast, die fast, seasons change. Environments shift, predators chase prey in constant cycles. But in the deep, those cycles barely exist. A single year can feel like a heartbeat. A decade can feel like a moment. Some deep-sea creatures take decades just to reach adulthood. Some reproduce once every few years. Some grow so slowly that scientists describe them as living in biological slow motion. The Greenland shark may be the ultimate example. It grows only a few millimeters per year. It reaches sexual maturity around the age of 150, and it may live more than 4 centuries. Measuring life in centuries, not years, is normal here. This slow pace is one of the reasons gigantism works so well. If your entire life strategy is conserve energy, then a large, slow, long-lived body is the perfect solution. One of the deep sea's greatest mysteries is only found during mass die-offs at the surface. When storms kill huge numbers of fish, when disease wipes out shoals, when ocean currents shift suddenly, dead animals rain down in massive quantities like a sudden storm of sinking bodies. And this is when deep-sea giants come alive. They gather from kilometers around, converging on the falling feast like ghosts appearing out of the dark. Giant isopods tear into carcasses, amphipods swarm in frenzies. Large eels twist through the remains, feeding until their bodies swell. These rare events may only happen every few years, but giants are built for exactly this moment. Eat once like a king, survive for months like a monk. Smaller creatures can never take full advantage of sudden abundance. Big bodies with large stomachs can. The deep sea rewards patience, and giants are the most patient animals on Earth. The pressure at great depths doesn't just shape bodies, it shapes entire ecosystems. At 1,000 meters, pressure reaches 100 atmospheres. At 4,000 meters, it reaches 400. At 10,000 meters, the depth of the Mariana Trench, it's over 1,000 atmospheres. This pressure crushes air, destroys gas-filled organs, shuts down enzymes, breaks down proteins, alters cell membranes. Any animal that survives down here must evolve structures that function in conditions lethal to most organisms. Giants often develop thicker exoskeletons, dense gelatinous flesh pressure, resistant internal chemistry, compact organ systems. And again, these structures scale better in large bodies. Evolution in the deep is like engineering under impossible constraints. Size becomes one of the few reliable solutions. In the deep sea, light works differently. Most of it isn't sunlight. It's bioluminescence, chemical light. Almost every deep sea creature uses it. Some to hunt, some to hide, some to lure, some to communicate. But giants interact with light in unique ways. The colossal squid has massive eyes because bioluminescence is the only clue it gets about predators like sperm whales. The big red jellyfish uses faint glows for slow communication or to confuse prey. Some giant amphipods grow reflective plates, turning into drifting mirrors in the darkness. Light becomes a language, a weapon, and a warning system. And for giants, larger eyes, larger organs, and larger surfaces help them detect or generate these signals in ways smaller creatures can't. Not all deep-sea giants are predators or scavengers. Some are something else entirely, living colonies. Giant siphonophores look like jellyfish but are actually huge chains of connected organisms. Some species stretch longer than blue whales, meters upon meters of transparent, glowing, drifting bodies. They move slowly, almost invisibly, through the deep, a floating living net. Each segment does a job. One part stings prey, another digests, another reproduces, another steers the colony. Together, they form one of the strangest giants ever discovered. If there is anything in the ocean that matches old myths of sea serpents, this is it. And their size only makes sense in the deep. No waves, no storms, no sunlight, no predators large enough to destroy them. The deep sea is one of the few places where a creature can stretch to unbelievable lengths without being torn apart. At hydrothermal vents, a different kind of giant thrives. Tube worms, 2 meters long, giant clams, large shrimps that glow with faint infrared patterns, bacterial matter spreading like alien meadows. These vents produce heat, chemicals, and minerals that never reach the rest of the ocean. They create miniature worlds where life can grow big, fast, and dense, even in the middle of darkness. The key difference: energy here doesn't come from sunlight or falling debris. It comes from chemistry, hydrogen sulfide, methane, and minerals erupting from the Earth's crust. Tube worms grow large because they host bacteria that convert these chemicals into energy. Their size is basically a biological real estate. The larger the worm, the more bacteria it can house. These are giants built not from scarcity, but from sudden abundance in a place almost no one can reach. Deep-sea giants feel invincible down in the abyss, but their strength collapses the moment they leave it. Bring a giant amphipod to the surface and its body ruptures. Bring a colossal jellyfish up too fast and it melts into a shapeless mass. Haul a giant isopod upward and its organs fail long before it reaches daylight. These creatures are engineered for pressure, cold, and darkness. Not sunlight, not warmth, not normal atmospheric conditions. Their size is only an advantage in the world built for it. Outside it, gigantism becomes weakness. This is why studying deep-sea giants is so difficult. Almost none of them survive in surface laboratories. Almost none can be transported intact. To understand them, we have to go to them, into the dark. For millions of years, deep-sea giants evolved undisturbed. But now, even the deepest parts of the ocean are feeling pressure, not from water, but from us. Plastic has been found in amphipods 7 miles deep. Fishing trawlers scrape the ocean floor, flattening ecosystems older than human civilization. Mining companies are preparing to drill the seabed for metals and minerals. Noise pollution travels farther underwater than we ever imagined, disrupting communication in species that depend on silence. The deep sea used to be a refuge, a place untouched by storms, climate, or human activity. That is no longer true. And the giants that survive millions of years of pressure and darkness may not survive a few decades of human interference. They are slow to reproduce, slow to grow, slow to recover. Damage done to the deep can last centuries. It's easy to look at these creatures as curiosities, strange animals hiding in the dark. But deep-sea giants aren't just biological oddities. They are key pieces of Earth's machinery. They recycle dead material that sinks from above. They regulate carbon storage on the ocean floor. They stabilize ecosystems that support global fisheries. They tell us how life can adapt to extremes, from pressure to cold to total darkness. Studying them helps us understand evolution, climate change, and even the possibility of life on other planets. If life can grow to the size of a car in a place with no sunlight and crushing pressure, then life elsewhere in the universe might be far more diverse than we imagine. Deep-sea giants aren't proof of how strange the ocean is. They are proof of how adaptable life is. The deep sea doesn't follow the rules of the surface. It doesn't reward the fastest. It doesn't reward the strongest. It doesn't reward the most aggressive. It rewards the patient, the efficient, the creatures that play the longest possible game. Gigantism in the deep isn't a mystery, it's a message. A message written in cold water, darkness, and pressure. It tells us that life always finds a way to survive, even when nearly everything seems impossible. It tells us that evolution never stops experimenting. It tells us that the ocean is not empty. It's overflowing with secrets we haven't even begun to understand. And somewhere in the blackness, drifting through water older than human history, there are giants we have not met yet. Creatures beyond imagination, shaped by worlds we have barely explored. The deep sea is vast, it is ancient, it is still unknown. But one truth echoes through its darkness. Life grows differently in places we never look.